Hello and welcome to lecture 10 of the course Computational Complexity. So in this lecture we are going to see co-NP. Okay, so just to summarize, we have already seen the classes P and NP. Right, P is a set of all computational problems or languages that can be decided in deterministic polynomial time, whereas NP is a set of all languages that can be decided in non-deterministic polynomial time. Right. And we also have the alternate characterization, right, which is like this. So a language is in P if there is a deterministic polynomial time machine such that it can decide it. That's in fact the same characterization. Whereas for NP we have this, it takes a different turn. There is this verifier characterization, meaning a language is in NP if and only if it has a polynomial time verifier. That means that for all x that is in the language, there should exist a certificate which can be verified, which can be used to verify the membership of x in the language. So the certificate should be polynomial in the length of x, and the verifier should run in time polynomial in the length of x, right? So that's what I've written here. It's a deterministic polynomial time verifier V such that x is in L if and only if there is a certificate y such that the length of y is polynomial in the length of x, and the verifier can verify the membership of x using y, right? So now let us define what is co-NP. Okay, so maybe I'll just push it a bit down. Okay, so what is co-NP? So definition: a language L is in co-NP, or rather, maybe I just write a different way. Co-NP is the set of all languages A such that A complement is in NP. Okay, so it is a set of all languages such that A complement is in NP. Okay, if you have a language A that is in NP, then or if you have a language A whose complement is in NP, then A is in co-NP. So co-NP is a class of all languages that are whose complement is in NP, right? So again, just one thing I want to say here. So caution: co-NP is not the complement of NP. It is not the set of all languages that is not there in NP. Okay, it is a set of all languages whose complement language is in NP. Right? It is not the complement of NP. So please, one may be tempted to think that it is a complement of NP. It is not, right? So some examples are SAT complement. So SAT is in NP. The complement language of SAT is SAT complement. Set of all Boolean formulas that are not satisfiable, right? Set of all pairs G comma K such that G does not have a K clique. So that's a complement of clique, right? These are examples of co-NP languages. These are in co-NP. Another example, okay, so this maybe it will take some time to figure out, or it will take some time to sink in, that tautology. Okay, so what is tautology? Tautology is a question where I give you a Boolean formula and ask Boolean formula phi such that is it always true regardless of what assignment you give to the individual variables in it. So this is unlike SAT, where you're asking is there some assignment such that it will evaluate it true. Now you're asking is this Boolean formula, no matter what you assign to it, is it always true, right? So this is an example of a language in co-NP. Why is it in co-NP? So you're asking whether phi is always true, right? So in other words, you're asking is so what are the languages, so what is the complement of this tautology, right? So again, this I am saying that tautology is in co-NP, right? I am saying that this is in co-NP. So what is the complement language of this? This is the complement language of this is the set of all Boolean formula such that it will not be always true. It will evaluate to false in some assignments, right? So if phi is not in tautology, that means it evaluates to false in some instances. So now if you take the complement of phi, right? So this is what I've outlined here as an exercise. If you take the complement of phi, then the complement of phi will have some assignment that evaluates to true, right? So phi is not in tautology means there is some assignment which will make phi evaluate to false, right? Because otherwise it will be in tautology, right? And that means that the complement of phi, right? So the complement means it's just flipping the evaluation. So phi does not always evaluate to true, and phi complement does not always evaluate to false, which means phi complement sometimes evaluates to true. In other words, it means that phi complement is satisfiable. So checking whether if phi is in tautology, the complement of phi is, or if a language phi is in tautology, whatever is not in tautology, its complement is insatisfiable. It's insatisfiability, right? So that is why tautology is a co-NP language, right? You are asking whether it always evaluates to true, regardless of what you assign to the variables. Another way to look at it, right, is this, right? So let's say L1 is in co-NP, right? We had this characterization. So you have this many different computation paths. A language is in NP if now how do we check if X is in L1 or some string is in L1? It should have some accepting computation paths. So there is one and there is another one, right? So there are accepting it has to have some accepting computation, right? Whereas if a language is in co-NP, then we want all the paths to be accepting, as is written here. All the paths should be accepting, none of the paths should be rejecting, right? So you can see why now why a language is in co-NP and its complement will be in NP, because if you take the complement, then all this will be reject, right? All the accepts, sorry, if you take complement, it will not be all accepts, which means it will have at least one reject. And if you take the complement of that language, that means that it has to have at least one accept, right? So what I'm saying is that L2 is in co-NP. The complement of L2 means that it cannot be all accept, right? If you put it on the same machine, it cannot be all accept. There has to have at least one reject. But that's the same as if you relabel reject and accept. It's the same as asking there has to be at least one accept, which is what we check in NP. Okay. So that is another way to kind of understand co-NP. And just like we had this kind of descriptions over here, the verifier based description, we have also a verifier based description for co-NP. So I'll write it here. L is in co-NP if there is a deterministic polynomial time machine V such that x is in L, okay, the complement of x, L is in NP, right? So this entire thing over here, that there x is y, etc., etc., this entire thing will be flipped. So for all y such that length of y is polynomial in the length of x, vxy will be 1. Right? So what is happening here is that here we want for all the y's, we have to, the verifier should evaluate to 1. So which is the same as saying here for all the paths we want it to be accept. Whereas in NP we just wanted one accepting path, right? Which is like the quantifier here in NP we say there exists quantifier, it's an existential quantifier. Whereas in co-NP we want a universal quantifier. So there is an inherent kind of difference, right? So here we want all the paths to be accept, whereas in NP we wanted only one accepting computation, right? Okay, now some points, co-NP completeness. So just like NP completeness, we could define co-NP completeness. So a language A is co-NP complete. So this is exactly like NP completeness. If 1, A is in NP, and 2, for all B is in it's not exactly like NP completeness in the sense that it is not always, we don't want A to be in NP, it is analogous. So we want A to be in co-NP. For all B in co-NP, we want B to be reducible to A. So this is exactly like NP completeness, except that A should be a member of co-NP instead of A being a member of NP, and B should be all B in co-NP should be reducible to A instead of all B from NP to be reducible to A, right? Some minor points, and I will stop this small lecture with that. So these are things that you could work out. I'll just give you high level ideas. So one is that A is co-NP complete if and only if its complement is an NP complete, right? So SAT complement, for instance, is co-NP complete because the complement of SAT complement is SAT, which is NP complete, right? Why is this true? What are the analogous requirements for NP completeness? The complement should be in NP, which is true by the definition of. So I'm just writing the NP complete definitions. A should be in NP. This is the NP complete definitions. And 2, for all B in NP, B should be reducible to A, right? These are the 2 requirements. So one, that A is in co-NP is satisfied by definition of co-NP. Then all the B that is in co-NP reduced to A. So we already have A complement is NP complete. So which means maybe I'll modify A complement is an NP and all B in NP reduces to, or let me use a different symbol, C in NP reduced to A complement. Now this means that consider all B in NP, right? B in co-NP. Now B complement is in NP, right? So B complement reduces to A complement, but the same reduction, if B complement reduces to A complement, that means B reduces to A, right? Because no maps to no, yes maps to yes. So you can work out the details. That's how this is done. Sorry. Second, P is contained in NP and co-NP. Why is this true? Well, we already know that P is contained in NP. Why is P contained in co-NP? Pretty much the same reason, right? So if you don't have any non-determinism, if you have a deterministic polynomial time machine, it is where there is no non-determinism, all the computation paths lead to accept. So you can think of a deterministic machine itself as a co-NP machine, deterministic polynomial time machine itself as a co-NP machine, right? So you have just to make a distinction, you have just this kind of thing, right? So this, if the language is in, if the string is in the language, then this is accept. If the string is not in the language, this is a reject. So if it is an accept, it satisfies this as well as this, the condition for NP as well as the condition for co-NP, right? So any language in NP is also in co-NP. Sorry, any language in P is also in co-NP. So again, you can write down the details of this. And another way to see it is that if a slightly long-winded way to see it is, if A is in P, then A is in NP. Sorry, a complement is also in P, right? If a language is polynomial time, then the complement is also in polynomial time, right? It's just flip the output. This means that a complement is in NP, right? Because P is contained in NP, which means that A is in co-NP. Right? This is another way to see the same thing. Again, in fact, I have written down the answer for you. Finally, if NP and co-NP are distinct, show that P and NP are distinct. Okay, so this seems like a tricky question, but it is easy once you see it in the contrapositive. So this is what we want to show. Instead, what we will show is, we will show P equal to NP implies NP equal to co-NP. So if, okay, this is what, and this I think is easier to show, right? So you can think about this. So because if P is in NP, P is equal to NP, that means all the languages in NP are also in P. If you take a complement of a language in NP, so all the, what is co-NP? Co-NP is a class of languages that are the complements of the languages in NP. But then NP is equal to P, and P is a class which contains its own complement. Right? If a language is in P, and if you take its complement, then the complement also will be in P. So for instance, if to check whether a graph is connected, is in polynomial time. To check whether a graph is not connected is also in polynomial time, because you could just take the same algorithm and just make accept into reject and reject into accept, right? So P is a class which contains the complements. NP is not such a class, or at least not as of now. But if P equal to NP, then NP will also be such a class, which means that co-NP will also coincide with the complement. So P equal to NP means NP and co-NP will also collapse to P. Hence, if P equal to NP, NP is equal to co-NP. So this implication is true, which means the contrapositive should also be true, which is what is given in the statement. Right. So we defined co-NP, which is the class of all languages whose complement are in NP. Once again, it is not the complement of the class NP itself. It is a class of all languages whose complement are in NP. Right? We saw the verifier based characterization. So we want X is in a language L which is in co-NP. If for all the certificates that you take, the verifier should be able to verify that X is in the language using all the certificates. Like all certificates lead to accept. In the computation tree form, it is like this: all the computation paths lead to accept. So the example are any language in NP whose complement. So SAT complement, click complement, and another language is tautology. So tautology is kind of like SAT complement, right? Just by flipping the yes and no. Then we defined co-NP completeness and saw some examples. With that, I will stop this small lecture. Thank you.